All right, chapter 8, getting ready to start into my favorite chapter, trigonometry. But before we jump right into the trig, we need to take care of some special right triangles. So there's two triangles today. We're going to learn about the 30, 60, 90. Tomorrow we're going to learn about the 45, 45, 90. They both have their little special properties and relationships that we can use to save ourselves a little bit of time along the way. And there's lots of different ways to teach this. I'm going to try to teach it using similar triangles, at least in the beginning. I may show you some shortcuts or tricks later in the chapter, but I want to kind of keep it similar to chapter 7 so we can build on what we've already learned. Alright, so example 1. First of all, there are two special right triangles. 30 degrees, 60 degrees, and 90 degrees. And then, like I said, we're going to learn the 45, 45, 90 in 8.2. We're going to pick that one up later. So let's first find the missing side. So since this is a right triangle, one method I could do is I could use the Pythagorean Theorem. So I'm going to use the Pythagorean Theorem to find this side over here. And let's just call this side x. So I'm going to work my Pythagorean Theorem here. X squared, leg squared plus leg squared equals hypotenuse squared, which gives me x squared plus 25 equals 100. I subtract 25 from both sides, which gives me x squared equals 75. And now I take the square root of both sides. And a lot of the times we will just go and punch it in the calculator and get a decimal. But I want to show you the simplified radical like we did earlier in the course. So I'm going to do it that way. So x is, I can break up the square root of 75 into a perfect square, the square root of 25, times the square root of 3. Remember, two radicals times each other can just make a bigger radical. And I can simplify this into 5 radical 3 because the square root of 25 is 5. Alright, so I just found the side length. The side is no longer x, it is now 5 radical 3. Alright, now I'm going to do this again for the second problem over here. And this problem, we're going to call this side x. And we start off solving it. So leg squared plus leg squared equals hypotenuse squared. So x squared plus 16 is 64. Subtract 16 from both sides and I get 48. And now when I take the square root of both sides, I get x equals, and trying to find perfect squares here, the biggest one I can find would be the square root of 16 times the square root of 3. And the square root of 16 is just 4. So it looks like I have my answer. It is 4 radical 3. Now, I did these two problems this way because I want you to see a pattern. Okay, because there's a pattern with problems like these. Alright, so I want you to see that there's a pattern. And the pattern kind of goes something like this. If you look at the side lengths, the smallest side, which is across from the 30, is 5. The largest side, which is across from the 90, is 10. And there's a relationship there. And if you notice, it happens on the other problem. The smallest side and the largest side. And the relationship is the hypotenuse is always twice as big as the smallest side in a 30, 60, 90 triangle. That's the relationship that you have to understand. The smallest side is always half the hypotenuse. Now, this other side, the medium side, or kind of the freak side I like to call it, that side also has a pattern. And if you kind of analyze it and you kind of look at it, you will see that it's just the smallest side multiplied by radical 3. It's the smallest side multiplied by radical 3. So that ratio holds true no matter how big or how small the triangle is. There's always that ratio. So let's scroll down a little bit. And this is going to allow us to set up some similar triangles. So the big idea from today's lesson is right here. Every single 30, 60, 90 triangle has sides with the following relationship. And this is the simplified version. This is the smallest triangle. So they're always in relationship of 1 to 2, and then the medium side, which is always the freak one, is the square root of 3. So that's the ratio. The ratio of the 30, 60, 90 degree triangle is always 1, square root of 3, and 2. And square root of 3 looks like it might be big, but when I actually break it down and I do the decimal for it, this really isn't important, but I just want to prove a point to you. This is about, 1.73. So it is the small, it is the medium, and there's the large. So I'm going to use this ratio, this known ratio for all 30, 60, 90s to solve other triangles, other bigger triangles. And then you might pick up some shortcuts along the way as well. So when you're solving one of these triangles, until you get good with the shortcuts, I would position another triangle the exact same way and label it, 30 and 60, and then use your ratio. So the smallest side's 1, the medium leg is 2, or square root of 3, and the biggest leg, the hypotenuse, is 2. And now I kind of have two similar triangles that I can set up a proportion. So if I want to find out what m is up here, I want to figure out, what's the size of m. Notice on this problem, I could not use the Pythagorean theorem because I only have one of the three sides. I need 2 out of 3 to do Pythagorean theorem. So I have to use another method. So here's how we're going to set it up. I'm going to do the big hypotenuse over the little hypotenuse, m is to 2, as, and then I pick the known sides, 4 is to 1. So I'm just using the same thing we did in the last chapter. I'm doing big over little and big over little. And when I cross multiply, I get m equals 8. Now, if you can memorize the shortcuts, you would have already known that the smallest side and the largest side is double. So you may have been able to do that without setting up a proportion. And then similarly, if I want to do it with k, I can put k is to the square root of 3, k is to the square root of 3, as 4 is to 1. And when I solve this problem, I cross multiply and I get k equals, when you multiply a whole number times a radical, you cannot multiply the 4 times the 3 because the 3 is inside that radical. So you just have to write it as 4 times the square root of 3 and leave it like that. And that also fits our pattern from the above example because, if the smallest leg is 4, we knew it was going to be that number times the square root of 3. But the proportion is kind of nice because you don't have to memorize, another trick or another pattern. So example 4, this time they give me the hypotenuse. So I'm going to set up my standard, my generic 30, 60, 90. There's 60, there's 30. So I always start with the smallest side, the hypotenuse, and then the freak side across from the 60. And now I can set up proportions. So I can say 18 is to 2 as f is to 1. And then to get g, I could set it up 18 is to 2 as g is to the square root of 3. And solving both of these, I will get 2f equals 18, which tells me f equals 9. So this is 9, which, knowing the pattern, I should understand that. The smallest side's half the hypotenuse. And this one, when I cross multiply, I'll get 2g equals 18 radical 3. And divide this side by 2. Divide this side by 2. Remember, I cannot do a number inside a radical with a number outside a radical, so I can only divide these two numbers, and I will get 9 square root of 3, which again fits the pattern that you should see. Okay, but it all kind of comes from drawing these little triangles down here with the known ratio of 1 radical 3, 2. All right, we're going to get a little bit tougher on this side over here where the numbers are a little bit weird. So if I just threw you an example like this one and said, hey, find u and v, the Pythagorean theorem would be kind of useless because I would have two unknowns. I'd have v squared plus 4 times radical 3 squared equals u squared, and I'd have two letters and I couldn't solve it. but now we should be able to. So let's draw in our generic triangle, always putting 1 on the small side and 2 on the large side, and radical 3 on the freak side. Notice I try to set it up to where it's the exact same position. Now I'm going to use ratios. So I'm going to say 4 radical 3 is compared to radical 3 as, and let's do v, as v is to 1. And I cross multiply here, and I get radical 3v, radical 3 times v equals 4 times radical 3. And now if I want to get v all by itself, to get v all alone, I divide by the square root of 3, and I divide by the square root of 3, which should just give me v equals, these two go away, and I get v equals 4. Now I could use a shortcut right now. Right away, if I know the small side's 4, I know this hypotenuse, this longest side, is going to be double that. So I'm already kind of knowing it's going to be 8, but I want to show you the actual setup to get it. So using proportions, similar idea. 4 radical 3 is to radical 3. I start off the same way as I did the last problem. Equals u is to 2. So I did big over little, big over little. And similar idea, I get the square root of 3u equals, and that bar should not be over the u, just the 3, equals 2 times 4 radical 3. Now really, you cannot do the 2 times the 3 because the 3 is inside the radical. This number can only be multiplied by that number, so I will have 8 radical 3. And divide both sides by radical 3, divide by radical 3, and you simply get u equals 8, which is what we knew we were going to get anyway, just by knowing the pattern. All right, number 6 is a little bit tougher because, I have the small side, and using the pattern, it might be tougher to see what double that is going to be, or what the square root of 3 times that's going to be. So I'm going to use the proportion again. So let's set up the little triangle right next to it, and I'm going to set it up again the exact same way. So I'm going to put this 90-degree angle right up here, and this is 30, so I have the smallest side, the hypotenuse side across from the 90, and the freak side, the medium side. And now let's just set up proportions. So let's find x first. So I'm going to say x is to 2, x is to 2 as 2 radical 3 is to 1. 2 radical 3 is to 1. Now I cross multiply, I get 1x equals, I can only multiply the 2 times 2 because the 3 is inside the radical, so 2 times 2 is 4 radical 3. So I found out what x is. It is 4 radical 3, which makes sense because that is double the baby side. It's double the smallest side. Let's set up the last one here for y. So I'm going to start off again. 2 radical 3 is to 1. And that should hold true with y is to radical 3. And this one's going to work out a little bit different, you'll see. So 1 times y is y. Now, when I do these two times each other, I can't multiply the 2 by anything because both of these numbers are inside radicals. So I just bring the 2 along. Now, the square root of 3 and the square root of 3 can be multiplied together because that number is inside the radical. So 3 times 3 is 9. So the square root of 9. But this can be simplified because this is really just 2 times, the square root of 9 is just 3. So 2 times 3 ends up being 6. So I now know that. So this one may not be quite as easy to see the pattern how you've seen in the previous triangles, because the freak side actually did not have a square root of 3 on it like it did on all the previous problems. But that's because the baby side had a square root of 3 on it. You're not going to see a whole lot like example 6. I'd say 90% of the examples are like 1 through 5. All right, we are going to do the last example. We're going to put it into kind of a regular geometry problem. Kind of a classic problem that you definitely are going to see on homework quizzes and on your test, and something everybody should be able to do by the end of this chapter. But find the area of an equilateral triangle. Alright, so let's digest that first. Area of a triangle is 1/2 base times height. So I had to know the area of a triangle. Now it's not just any triangle, it's an equilateral triangle, which means I have 3 equal sides, 3 equal angles, and since it has that up to 180, they are 60 degrees each. So let's draw this thing. So I have my best sketch of an equilateral triangle that is 60, 60, 60. It tells me in the question that it has a side length of 4 feet. So you're 4, you're 4, and you're 4. So now the formula, trying to run this formula up here, the base is not too bad. You know, the base right here is just the bottom piece, which is 4. So the formula starts off not too bad. I have area equals 1/2 base times, and here's where the tough part is. The tough part is what the heck is the height? And the height is going to be drawn in right here. There is the height. It's the altitude coming right down at 90 degrees. Now in an equilateral triangle, that altitude splits it into 2 equal pieces. And luckily for us, it splits this top angle into 30 and 30, which makes it a special right triangle. So now I should be able to solve this thing. If you look at it, on the bottom, that 4 gets split into 2 pieces. You know, I have 2 and 2 because that 4 got split in half. So ultimately, if I just kind of focus myself on this triangle here on the right side, you could do the left one as well, but if I just focus on that, here's what I have. I have a 30-60 triangle where I'm actually missing the freak side, and we're going to call it H. This is the height. I'm missing that freak side. But I know a couple of sides now. I know that this side was 4 from the original picture. I know that this little side is 2. And so now I can either use my pattern, I could use the trick to find H, or I could do what I've been doing, and I'm gonna do it this way. I'm gonna set up my old original 30, 60, 90, where the smallest side across from the 30 is 1, the biggest side's 2, and the freaky side, the middle side, is the square root of 3. And I'm going to use proportions. So I do my little proportion down here at the bottom, and I'm going to say H is to square root of 3 as, and I have choices here. I could do 4 is to 2. I could have also did 2 over 1. It really doesn't matter. Probably would have been easier to do 2 over 1, but who cares? I'll multiply this. I'll get 2H equals, remember you can't do 4 times 3, you just have to write it as 4 radical 3. To get H by itself, I'm going to divide both sides by 2 and cancel some things out, and I get H equals 4 divided by 2 is 2 radical 3. Now you might have a long time ago said, hey, I know the small side's 2, the big side's double, and the freak side you just multiply by the square root of 3. And if you know that, then don't do all this solving proportions work. But some of you may not see that pattern right away. It takes a little bit of time. So now I can finish the area formula and answer the question. 1/2 times 4 times 2 radical 3. So the radical 3 I can't do anything with. There's no other radicals to multiply him with. You know, he's almost like a variable. I can't do anything with him. But now the other numbers, 1/2 times 4 times 2, well that's 1/2 times 8, which is just 4. So the area of the triangle is 4 radical 3, and our units were feet. Now this would be the exact answer. This would be something that the SAT or ACT would probably prefer. We could actually multiply this one out and get 4 times the square root of 3, and that is approximately about 6.928 feet. So if I were doing a real life project and I said, hey, how much paint's it going to take to cover this 4-foot equilateral triangle, I would need to get enough paint to cover about 7 square foot, roughly. So, but make sure that you can do the approximate answer or the exact answer. And the SAT definitely is preferential to radicals and not changing them into decimals. All right. Well, hopefully you got enough to get you ready for the practice tomorrow. See you.